All right. So that assignment that I've just given you is due, I've got the dates not right, on Wednesday the 19th. So that's a week from today. I've got it right in Blackboard, but just not on the screen. So you've got a week for that one. I had printed a course schedule for you, but I got the date of spring break wrong, and that's probably the most important date of the whole semester. Second place would be the final exam, I guess, but so I'll make an adjustment to that and bring printed copies to you on Friday. Although 4:33 on Friday will be virtual, this class will be live. So if you're wondering, if you're in both, we will have our normal live class meeting on Friday of this week. We're going to continue talking about some concepts from chapter 7 in the book. Hopefully, if you don't already have it, you've at least placed the order for the textbook. I think it's really important that you get a copy of that and read it because it's not that lengthy, but the author does a great job of explaining concepts in a way that's a little bit different from me. And I think between the two, me and the textbook, you'll have a good understanding. Remember that what we did on Monday was we looked at the Moody diagram. And we went through the process of determining the friction factor that should be used given some specified flow conditions. So this is a figure that characterizes the resistance to flow. We're going to talk about resistance to flow in a little bit more fundamental terms today and discuss what are the forces that cause that resistance to flow. You will use this Moody diagram in the homework assignment I've just given you, problem number 8. It says use the Moody diagram to determine the applicable friction factor. And so very similar to what we did in class on Monday, you'll go through the process of finding out what's the velocity of flow through the pipe, because this problem tells you the flow rate, 1,000 gallons per minute. And we know the pipe diameter, 12 inches. So from that you can find the velocity. We know the water temperature, and so from that you can get the kinematic viscosity, and those are the things that you need to know to determine the Reynolds number. And so you'll go through that process of knowing the relative roughness of the pipe and the Reynolds number, intersecting the curve, and then going to the left to determine the friction factor. So that's how you should determine F on this problem. Now, let's look at an element of water that's flowing through a pipe. So this is a control volume, and this isn't the pipe itself. What we're looking at is the water that's inside the pipe. And so what we're going to do is consider the forces that are acting on the water inside this pipe and that the water itself exerts on the pipe. Okay, so to the left of this element of water, the water that's on the other side of it is pushing in. So P1 times A is a hydraulic force that's pushing this water towards the right. And in this case, water's flowing from 1 towards 2. And so the water is going from the left to the right. And so this is one force, the water that's also in the pipe, but to the left of this particular system. Similarly, P2 times A is a force of the water that's on the other side of this element of water, and it's pushing to the left. Okay, so those are both acting along this length. And what we're going to do is a force balance. And so in the direction of flow, we want to see what's the equilibrium. So P1 times A is to the right, P2 times A is to the left, and so that's why here in this force balance, where we're doing the calculations, the minus sign is in front of the P2 times A. Okay, this amount of water has a weight that's acting downward. And so if we were to calculate the volume of water, we could do that with multiplying A times L. So A means the cross-sectional area, and L is the length. And so A times L gives us the volume of water in this system, and then multiplying it by gamma gives you the weight, because gamma, of course, is the unit weight. wonder how I can move this thing, because it's not really helping me at all. Well, I'll figure that out next time. All right. So the other force that's here, the last one in this equation, is, oh, now my mouse doesn't work. There it is. The last one is the shear stress. So the shear stress is the resistance to flow. And look at the direction of that. If the water's flowing from 1 towards 2, so that means the water's flowing to the right, we know that the resistance is going to be opposing that movement. And so the force of the shear stress applying from the pipe to the water is in the leftward direction. And so the magnitude of that force would be the perimeter times the length. So the outside perimeter times the length gives us the surface area of the water. And then multiplying that by the shear stress, remember units of shear stress is newtons per meter squared. So if you multiply the shear stress in newtons per meter squared by the outside area, then that gives you an idea of what's the magnitude of the resistance. How many newtons of shear stress resistance is there to the rightward flow? And it's that resistance that causes the pressure change in part between location 1 and location 2. Part of the pressure change, of course, is that they're at different elevations, and there's the hydrostatic effect. But part of the pressure change from 1 to 2 is because there's resistance to flow, friction. And the friction expresses itself as this shear stress that's opposing the movement. Okay, so this equilibrium can be done, and we know that equilibrium means that all the forces are balanced for steady flow. Steady, uniform flow means that the flow rate isn't changing with respect to time, and since the diameter is constant, there's no change in velocity with respect to position as well. So steady, uniform flow. Now the change in pressure divided by gamma, that's the definition of H sub F, the energy loss due to pipe friction. So if this is a horizontal pipe, then the only thing that's going to be causing the change in pressure is the energy loss due to pipe friction. Now, R is hydraulic radius. And the reason why we invoke that is that if we know for a circular pipe, for example, and we want to determine the relationship between the energy loss due to pipe friction and the shear stress, then this formula will allow us to do this. We've rearranged, substituting in the change in pressure, and accounting for it being a horizontal pipe. If it's horizontal, then the weight of the water is acting downward, and it's not influencing the force equilibrium between 1 and 2. This is showing it inclined, but if alpha is 0 and the pipe is horizontal, then the weight term here isn't in the equation. Okay, so if you have a hydraulic radius, let me just define this on the board. Of course, we know, like for a circular pipe, for example, that the area is pi d squared divided by 4, right? And then the perimeter of the pipe is pi d. That's the perimeter of the pipe. Hydraulic radius, the definition of that is area divided by the wetted perimeter. And so if we were to divide these two, pi d squared divided by 4 divided by pi d, all that's left is d divided by 4. So the hydraulic radius for a circular pipe is d divided by 4. So the step between this formula and this one was substituting in d divided by 4 in place of r. So that leaves the d in the denominator and flips the 4 up into the numerator algebraically. So what we end up with is a relationship between shear stress and S sub F, which is the slope of the energy grade line. And I hope what you remember from last semester in fluid mechanics is that if we have water flowing through a pipe, then there's this imaginary line above it, the EGL, energy grade line. And what that is it's the elevation and the pressure head and the velocity head. So it's kind of like a representation of how much energy is in the water. It's that line that's above the pipe itself. And so the slope of the energy grade line, S sub F, is talking about how steeply sloped is that imaginary line above the pipe that represents how much energy is in the water. You'll use this formula in the homework assignment to relate the slope of the energy grade line to the shear stress. All of this that I've showed you so far has been for a pipe that is enclosed, where the water is inside a circular conduit. If you have open channel flow, meaning it's water going through a river and it's not pressurized, then there are similar considerations. We've got the energy grade line. Here they're referring to TEL, means total energy line. Just different texts have different definitions, but it means the same thing. It's the elevation, the velocity head, and there's this imaginary line that's representing the amount of energy that's in the water. But we have the same thing where there's a shear stress, a resistance to flow movement here, and you can see the shear stress is in the opposite direction of the water that's moving from the left towards the right. In an open channel flow, if we have steady uniform flow, then the channel slope and the water slope and the slope of the energy grade line would all be parallel. But they're not parallel in the case of a water pipe, because a water pipe could be horizontal and still have water flowing through it. If you have a river that's horizontal, the water's not going to move anywhere, because it's the downward slope that provides the energy for the water to flow in a river. In a pipe, what's providing the energy for the water to flow is a change in pressure. It's not the slope of the pipe itself. Okay, so just to get some practice playing around with the ideas of shear stress, let's look at this example of a pipe that's inclined. So the water is flowing from the left to the right, but it's going upward through a pipe, which is, it's possible in a pipe, but it's not possible in a river, at least not for very long, for water to flow uphill. So here we have an upward inclined pipe, and we know this physical slope of the pipe is 0.1 meters of vertical for each 1 meter of horizontal. The shear stress is known to be 45 newtons per meter squared. And so we want to calculate from that the slope of the energy grade line, S sub F, and then how much would the pressure change in a 100-meter pipe. So for part A, we're just going to be substituting into this formula. But for part B, where you're finding the pressure change, you'll need to use the energy equation, which is here on the screen. And so I'm going to pause for a moment and ask you to calculate what is S sub F for the pipe that's described. And remember, R stands for radius, and if it's a circular pipe that's flowing full, then the hydraulic radius is just the diameter in meters divided by 4. So the first thing we want to do is rearrange this to solve for S sub F, the slope of the energy grade line. And in a sense, this is kind of an artificial example because you can't directly physically measure the shear stress of the water. That there isn't a sensor that you can dip into the water and measure the shear stress. And so this is just kind of an abstract example to get you acquainted with applying this formula and understanding what the different parts are. But let's say that we did know the shear stress of the water in the pipe, and from that we want to know the slope of the energy grade line. So here you can see that the first thing that I've done is, if I didn't know the d divided by 4 shortcut, if I just wanted to define the hydraulic radius as the area divided by the wetted perimeter, then I get that the hydraulic radius is 0.0375, because here's the area that you'd get for a pipe of 150 millimeter diameter. Here's the wetted perimeter that you'd get. And it's the same hydraulic radius if you do apply this shortcut of just being d divided by 4. So we've got the hydraulic radius. Having rearranged the shear stress equation to solve for S sub F, then that means that the slope of the energy grade line is 0.12232. So that is, in the direction of flow, the slope of the energy grade line. Here I've got the pipe sketched up on the whiteboard. Let me just kind of show what the energy grade line would be doing. The energy grade line is going like this. It's going downhill in the direction of flow. So the flow is going from the left to the right. It wouldn't do that if the energy grade line wasn't going downward. That's what's driving the flow. In the same way that water flows downhill, like you can visually see it, in a pipe, water could flow uphill if there's a pressure differential. And so this energy grade line slope is a representation of the pressure differential between the two locations. And how steep it is a reflection of the amount of shear stress that the pipe is applying to the water. Okay, so as I circulated around, I saw lots of people had calculated 0.122 meters per meters, so it's unitless. That's talking about meters of vertical per meter of horizontal length. Now, one of the things I have noted here is that the slope of the energy grade line and the physical slope of the pipe are independent. You can have a pipe going uphill, and you can have an energy grade line going downhill. In an enclosed conduit, that is possible. In fact, it happens a lot. You know, the water may come up the hill to your house, even though the water line is at the road that's at a lower elevation. Okay, this next part. What is the pressure change over 100 meters of pipe length? Okay, so for that, what we need to do is start with the energy equation. You can see that I've suggested let's have Z1 be 0 and Z2 would be 10, because the slope of the pipe was defined in this problem as 0.1 meters of vertical per meter of horizontal length. So here, this 100 meters of pipe length is effectively talking about horizontal length. You know, there is a hypotenuse here, but we don't have to worry too much about differentiating between horizontal length and inclined length. And I'll show you a proof of that in a few lectures, but they're so close together that we don't need to distinguish between the two. Okay, so here, the velocity at 1 and the velocity at 2 are the same because it's a pipe diameter of 0.15 meters that isn't changing. So there's no non-uniform flow. The flow is uniform, so V1 and V2 are equal. You can see I've canceled them out of the energy equation. Z1 is 0, Z2 is 10. So I'm just rearranging this equation to isolate on the left-hand side P1 minus P2. So that change in pressure is going to be gamma multiplied by the elevation difference, so Z2 plus the energy loss due to pipe friction. So those are the two reasons why the pressure is going to be lower downstream. So think about location 2. Like even before you started doing the calculations, would you expect that the pressure down here at location 2 is higher pressure or lower pressure? Well, both of the things that's causing a change in pressure operate in the same direction, because the hydrostatic effect is saying the pressure is going to be less at 2 because it's higher up in the fluid. Remember, as we go down through the fluid, the pressure is higher. As we go up through the fluid, the pressure is less. So that's part of it. Then the other part is what's the effect of pipe friction. And so since location 2 is downstream, it's also going to be losing energy and losing pressure because of pipe friction. So both of those things combined will make the pressure at 2 lower than the pressure at 1. And that's what we have here, is that we can anticipate to see a drop in pressure of about 218 kilopascals over this 100-meter pipe length. Any questions about that? Okay, I think that in the homework assignment you have a problem that's similar to this, where you're having to play around with the shear stress equation to find the relationship between shear stress and slope of the energy grade line. So hopefully that example will kind of give you a nudge in the right direction for that homework problem. Okay, so in fluid mechanics, it's not until we got towards most of the end of the semester when we got into Chapter 7 and talked about the energy equation. Earlier than that, we used the Bernoulli equation to tell us how pressure changes in a situation where there is non-uniform flow. So this picture on the left just shows the Bernoulli effect, where, remember, you have a reduction in, I can't see my mouse, it's hard, but there it is. I'll just use my finger to gesture. If you have a small diameter pipe, the velocity is fast. If it's transitioning to a large diameter pipe, the velocity is slower, and the change in velocity caused a change in pressure. So the Bernoulli equation was able to account for that change, but the Bernoulli equation would have nothing to say about a pipe like this where the diameter isn't changing. The Bernoulli equation is just looking at changes in velocity and predicting the pressure change because of a change in velocity. But in a constant diameter pipe, there is no change in velocity. But we know that there will be a change in pressure because of the effect of pipe friction. So the difference between these two formulas, the Bernoulli equation and the energy equation, is that the energy equation no longer assumes that the flow is inviscid. And it starts to account for the reduction in pressure due to pipe friction. So delta P is more effectively accounted for in the energy equation. And so a big part of this semester, maybe one of the driving questions that we're going to be trying to answer is, how does the pressure change in different situations, depending on how long the pipe is, the diameter of the pipe, adjustments in flow rate. We're going to be a lot of the time trying to predict the downstream pressure, and then in the design make adjustments to the pipe characteristics to make sure that the pressure is within an acceptable range, so that an adequate flow rate of water can be delivered to our target, so that people have enough pressure when they're trying to shower and consume the water. So a big part of the course is just applying the energy equation to predict the downstream pressure. One way for us to measure pressure changes is a piezometer. And you'll remember from fluid mechanics that a piezometer is just a simple way of measuring the pressure, because all it is effectively a puncture in the pipe connected to a tube. And the water level will rise to a certain elevation to reflect how much pressure there is at that location. And so this pipe segment that's shown, if we had a certain length of pipe and the water level isn't rising as high in the piezometer on the right, then that would be an indicator of the flow direction. For one thing, we'd know that the water's flowing from the left towards the right. Otherwise, there wouldn't be that deflection. But H sub F is physically manifested. H sub F is the energy loss due to pipe friction. So this is how much energy there was upstream. Downstream, there's less energy, and we see that there's less energy because it's not rising as high. So H sub F is how much energy was lost between those 2 points. So hydraulic grade line is the pressure head and the elevation head, and that's what a piezometer is showing, is the hydraulic grade line. If we want the energy grade line, then we have to add in the effect of the velocity head. So the energy grade line would be above that. But the piezometer itself traces out the hydraulic grade line. And the HGL goes down because of pipe friction. And the Darcy-Weisbach equation is why we were looking up F values out of the Moody diagram to determine F. It's the factor that tells us the relationship between the characteristics of the pipe, how rough the pipe is, and what Reynolds number there is for the flow, that F value relates the other characteristics of the pipe, like the length of the pipe and the diameter, to the amount of energy loss that's going to be experienced, H sub F. So on the left here, we're saying the energy loss between the 2 points, the change in pressure head and elevation, is accounted for by the energy loss due to pipe friction. So that's where the Darcy-Weisbach equation comes from, is just measurements of different pressure losses. And if we have a pipe that's enclosed, the physical slope of the pipe, which is S naught is just referring to the pipe itself, where S of F is referring to the slope of the energy grade line. The two are independent. The S of F can be downhill and the pipe could be uphill, like the example we just looked at. Here, this pipe is downhill. The water's flowing downhill, but it's going to be a different slope than the physical slope of the pipe. The slope of the energy grade line doesn't have to be the same slope as the pipe slope. One of the brief detours that your textbook takes is something called shear velocity. Shear velocity, which is V star, is just a way of conceptualizing of shear stress. Instead of newtons per meter squared, you can rearrange shear stress and express it in terms of meters per second, so units of velocity. And what it comes from is just the idea that energy loss due to pipe friction is related to shear stress. So this equation on the left, we know that that's how you could calculate H sub F. But in reality, H sub F is calculated using the Darcy-Weisbach equation because we don't have a way of physically measuring the shear stress. So if we combine these two things together, then it relates the friction factor F and the shear stress. And if you look at the units of the left-hand side of that equation, so shear stress divided by density, then the units end up being meters squared per second squared. And so that's just when someone thought, well, let's call that shear velocity squared. And so then shear velocity would be the square root of that term, shear stress divided by density. And so then that gives you meters per second. So I think in the homework, just to cement your understanding of shear velocity, you may need to use this formula where you know the friction factor for a pipe, you know the velocity of the water that's flowing through the pipe, and then you could calculate the shear velocity, which is just another way of expressing how much shear stress exists in the water. So this formula that's in the box is what you'd use for that. By the way, I don't remember if I already announced it because I've got 2 classes back to back, but the lecture notes are posted online. So you can get those. They're not posted online? Okay, well, I'll have to look because I uploaded them, but maybe they're not visible yet. I've got them ready. They'll be posted online today. Okay, so all of this has been closed conduit flow, but we're talking about flow resistance in general terms, kind of like the fundamentals of shear stress and energy loss, and a lot of those same fundamentals also apply to open channel. And here is a trapezoidal channel. You're going to spend a lot of time this semester pondering the geometry of a trapezoidal channel. And so this is a front view of water flowing through a channel where the top width is greater than the bottom width. And the reason why trapezoidal channels are so common is that soil will cave in if you try to make a perfectly rectangular channel like this. You could do it with concrete or rock, but if you did this with clay or sand, it's going to cave in and naturally kind of form this trapezoidal shape. And so in nature and also in constructed channels, it's pretty common to have this trapezoidal shape. And so the way that we describe the geometry here is the bottom width is lowercase b. Depending on what formula you're looking at, the top width is either assigned a capital B, which is our textbook, or a lot of the formulas that are in the FE reference manual are in terms of they use the capital T for the top width. And then the side slope is 1 unit of vertical to T units of horizontal. So that's how you'd say how steep it is. And so if it was a 2-to-1 side slope, meaning 2 units of horizontal to 1 unit of vertical, then we'd say T equals 2. And what we sometimes want to know is, for a certain flow rate, Q, what is going to be the depth, Y? So, we're going to be solving for the depth, and the geometry of this trapezoidal channel will be part of the hurdles that we'll go through to find that flow depth. So the same flow resistance equation that relates the shear stress to the slope of the energy grade line, it also applies here in an open channel flow. And if you have an open channel, though, for steady uniform flow, the slopes are equal. I've mentioned this once already today, but I'll say it again just to emphasize, is that the bottom of the channel, so the channel bed slope is parallel to the surface of the water, and the water surface is parallel to the energy grade line. And so those three slopes are equal because the surfaces are parallel. So the slope of the energy grade line would just be the energy loss divided by the length of the segment. Okay, how much time do we have? 5 minutes. That'll be enough for us to just do a quick look at the geometry of this channel. So it's trapezoidal, and we want to know what is the hydraulic radius of the channel in terms of the bottom width, the flow depth, and the side slope. So like if we were going to try and substitute into this formula, what is R in terms of Y, B, and T? So let me show you this. Remember hydraulic radius, the definition of that is area divided by wetted perimeter. That is hydraulic radius. Some books will just call the hydraulic radius R, and some books call it R sub H for radius hydraulic. So I may accidentally put R sub H sometime when I'm writing on the board just because I've used so many books that use that notation. But the hydraulic radius is the area divided by the wetted perimeter. And there again, area divided by the wetted perimeter. Sometimes they'll say P sub W, wetted perimeter, but it just means wetted perimeter. All right, so the area, think about a trapezoidal shape like this. What is the area if we know B, this is Y, and then it is 1 to T is the side slope. So the way that we can determine the area is B times Y plus Y times T times Y. Because what we'll have is a rectangular section. So B times Y is this first rectangular section. And then we want to know what is the area of these sides. And so the area of the sides is Y times T, and that gives us this length, and then multiplying it by the depth, which is Y. And so the two of them together, this is just a triangle, and if you put the two triangles together, you've got another rectangle. Okay, so that's the area. The wetted perimeter is even a little bit more tricky because what we're trying to figure out is, like, what is this distance for the wetted perimeter? And includes this little segment here has a length of y squared plus ty squared. And so that is one of them on this side, it's going to be both the right and the left. So the wetted perimeter is B, so that bottom distance, and then the two side slopes. So B plus 2 times the square root of y squared plus ty squared. And we could factor out the y from there. So it's b plus 2 times y square root of 1 plus t squared. Okay, so hydraulic radius, what are we left with? The hydraulic radius is going to be by plus ty squared divided by b plus 2y to square root of 1 plus t squared. So I would suggest making sure you have that written down in case it comes in useful for the homework assignment, but it's just the hydraulic radius in terms of the other geometric parameters. All right, 1:49, we're out of time for today. So what I'm going to do is I'm going to post the notes online. I'm going to post the updated schedule online that has the correct spring break date. And we will meet in person on Friday. I will see you then.